Calculus is about functions. We define the word and we use the word. I start with 3 examples: linear function y x equals sine 2x, squaring function y x equals sine x squared, and exponential function y x equals sine 2 to the x. These 3 functions increase when x is positive, but at different rates. The linear function increases steadily, the squaring function increases faster as x grows, and the exponential function increases even more rapidly after some point. Calculus studies growth rates, and we focus on pairs of functions, the original function and the growth rate function. For example, the growth rates are dx 2 for y equals sine 2x, 2x for y equals sine x squared, and 2 to the x times natural log of 2 for y equals sine 2 to the x. The slope of a graph is the ratio of change in y to change in x. For linear functions, this slope is constant. For y equals sine 2x, the slope is 2 everywhere. The slope tells us how steep the graph is and connects to concepts like speed or growth rate. At a single point, the slope is found as a limit of average slopes as we consider smaller intervals. For y equals sine x squared, the slope at point x is the limit of change in y over change in x, which algebra shows equals 2x. The tangent line touches the curve at a single point and gives a linear approximation to the curve near that point. For y equals sine x squared, the tangent line at x0 has equation y0 equals sine 2x0 x. The second derivative tells us about the bending of the graph, whether the slope is increasing or decreasing. For y equals sine x squared, the second derivative is constant 2, indicating the graph is curving up. The derivative of power functions y equals sine x to the n follows the pattern dy dx equals sine n times x to the n minus 1. This rule works for all powers, including negative and fractional exponents. The slope of the sine curve y equals sine x is the cosine function dy dx equals sine cos x. This connects trigonometric functions through differentiation. The exponential function y equals sine e to the x is the unique function whose derivative equals itself. Dy dx equals sine y. This solves the differential equation dy dx equals sine y. Starting from y equals sine 1 at x equals sine 0. We construct e to the x as an infinite series, 1 plus x squared over 2 plus x cubed over 6, and so on. Adding infinitely many terms defines e to the x precisely and shows why its derivative equals itself. Multiplying exponentials follows the rule e to the x times e to the x equals e to the x plus x. This matches the addition of exponents and holds for all real numbers. General exponentials like y equals sine b to the x can be expressed using e. B to the x equals e to the natural log of b times x. Their derivative is the natural log of b times b to the x. Euler's formula relates complex exponentials to trigonometric functions. E to the ix equals cosine x plus I times sine x, connecting exponential growth with oscillation. Continuous compounding describes how interest grows continually, leading to the limit definition of it arises by taking the limit of 1 plus x over n to the n as n becomes very large. The differential equation dy dx equals sine ay has the solution y equals sine e to the ax, generalizing exponential growth or decay depending on the sign of x.